All right, welcome. It's time to start up again. Now we're going to be talking about mass moment of inertia. We're done with area moment of inertia, other than you'll have some problems to consider with that. Mass moment of inertia is much more what I'm going to be focused on during the semester. Again, the area moment of inertia was more of a service part of the course. So going now to mass moment of inertia. So here we have a blob. And so relative to the z-axis, we'd like this blob to spin around the z-axis. Okay, and so I have a radius distance out to some differential mass. So what is the distance, radial distance off of the axis for spinning? All right, our equation relative to z. And sometimes I'll note that to distinguish between area moment of inertia and mass moment of inertia, people will do something like the following. They'll say IZZ, and the double Z's indicate you're dealing with mass moment of inertia. I'm not going to bother with that because for the rest of the course, I only care about mass moment of inertia, and that's just a nuisance to have to bring all those along. So IZ equals the integral with respect to mass of r squared dm. Very similar equation. Has the same basic form as what we just did. And in some cases, these are very related. Why do I say that? So I'm going to compare this to area moment of inertia, and let's make a few assumptions. Starting from here, let's suppose the density is constant over the mass. If the density is constant over the mass, I can do this. I can rewrite differential mass as density times dV. Absolutely accurate. And so if this is a constant, I can then factor that out. No problem. Now, let's suppose that this differential volume is some constant along one dimension times a differential area. What am I saying? This. So I can write dV as some constant times dA. So we have just in one dimension, everything is just constant length, as it were. Call that K. Okay, put that in here and factor out the K. I have rho K r squared dA. So that's actually the polar moment of inertia from what we had for area, times this rho times this K. So these are, under certain circumstances, they can all but be the same thing. You have to add some constants, but very close. All right. So once again, we're going to have the concept of the parallel axis theorem here. So let's start bringing that in. And so here, how does that work? So given the mass moment of inertia at the center of gravity, or center of mass, same difference, so here it is at the center of mass. So given this, we can go to any other axis for rotation. So this is the axis we care about. Start from the mass moment of inertia at G, and then plus mass times distance squared from this axis to that axis. Same equation. Okay? Now there's one more concept that we have to bring in here that's very common out in the real world. And we're going to talk about the radius of gyration. All right? And so what is that? So suppose I have an object and I get its mass moment of inertia. And I know its mass. So the radius of gyration is defined this way. Take this, that is equal to mk squared. So there's mass, and k is the radius of gyration. And this can get confusing because you can have problems with springs, and so you can wind up having mass moment of inertias and springs and k's and all sorts of things going on. Have to just watch the context. So our mass moment of inertia relative to the center of mass is equal to mass times the radius of gyration squared. All right, so if you have the mass, you have the mass moment of inertia, you can simply solve for k, and that's it, this right here. Now, in practice, it goes the other direction. So it is not unusual when you get parts out in the real world that it will come with specifications or properties they've mentioned. And so they won't tell you the mass moment of inertia of the part, but they will tell you instead the radius of gyration, and they will tell you its mass. So picture what they'll do is you buy a part, they can put it on a scale, and they can determine the mass. All right, and then they can basically spin it, and a machine will tell them the radius of gyration. And so then all you have to do is say m times k squared, and now you know the mass moment of inertia. Okay? So this is often a specified property for something. All right? So when you get k, square it times mass, bam, you have the mass moment of inertia, which is what you need to use Newton's law. All right. Now, what does this reflect? Okay. I say this here. It reflects mass as an ideal shell or pipe where all of the mass is at radius k. Putting that really simply, once you compute this, the radius of gyration says that if you could make a pipe, so there's a pipe, R, so think what a pipe is. It has all its mass at the radius of whatever the pipe is. Okay, so let R equal k. So what this is saying is if you were to take whatever device you have, this is saying it's equivalent to a pipe of radius k where all its mass is right at that radius. Obviously in practice, if you have a pipe, the walls have thickness. So what I said here, going back down, is it's an ideal shell or pipe where all of the mass is exactly at radius k. That's what the radius of gyration basically means. Finding an equivalent pipe to whatever it is that you have. All right. So let's put some of this to use with a little problem. This is a problem that's been on exams in the past, and quite frankly, it's caused people grief. So, and usually when problems cause people grief, that's a sign to me that I need to put the problem into the lecture, because there must be a concept they're having trouble with. So let's see what I have here. I've got a plate that's kind of bizarre shaped, but that's okay. And its total mass is given as 20 kilograms. Its mass moment of inertia, you can tell because it's kg meters squared, is the kg shows there's mass there. It's not meters to the fourth. So I have 140 kg meters squared here at A. And 1 foot away from A is B. I'd like to get the mass moment of inertia at B. So picture A is an axis coming out. So here's my pen, and let's do it this way. So you can see my pen rotating. So that's what we're getting. The mass. We have the mass moment of inertia about A. I'll move down to B. We'd like the mass moment of inertia about B. How do we do that? It's a trick problem. All right. Here's what's happened on many exams. They get this, and so they say, bam, got that. And so then they'll do md squared, where d is 1 foot in this case, and go to B. And they're dead wrong, and they get no credit. All right. The parallel axis theorem only works from the center of mass with respect to mass moment of inertia, the centroid in terms of area moment of inertia. Here I'm dealing with mass moment of inertia. And here we're told that's the center of mass. So to get to B, what I have to do is go from A back to G, then I can go from G over to B rather. So that's the key to the whole problem. So IA, which I know, is IG plus, if we had that, the mass times the distance to there. All right. Well, mass, we're told, is 20 kilograms. Distance, 1 squared plus 1 squared, so it's distance squared. Okay, that just works out to 40, so 140 equals Ig plus 40, so Ig is 100 kilogram meter squared. Once we have that, it is then just a joke to move from G to B. Ig is 100, mass is 20, and now we just need the distance to go from G to B. And if we just come here, we can see that's down to over 1. So that would be 2 squared plus 1 squared. And we don't have to square root it because it's distance squared. So 100 plus 20 times 5. Bam, we have 200 kilogram meters squared. And you see this number, as we get away from G, farther we get away, the bigger the number is going to get. All right, we're going to stop right there. And next time we're going to start computing mass moment of inertia for composite parts. See you then.